Hello, everyone. Welcome to our new event. Today's topic is Basic Knowledge of PLC. Welcome to the fascinating world of PLCs, the unsung heroes powering factories around the globe. Today, we're diving into the brain behind modern automation. Whether you're an engineering student, industrial worker, or just curious about how things work, this video will give you everything you need to understand programmable logic controllers. What is a PLC? A Programmable Logic Controller, or PLC, is essentially an industrial computer designed to control manufacturing processes. Unlike your laptop or smartphone, PLCs are rugged computers built specifically to survive harsh factory environments, withstanding extreme temperatures, electrical noise, vibration, and impact. Think of a PLC as the conductor of an industrial orchestra, coordinating countless instruments to create a symphony of automation. It takes inputs from sensors, processes that information according to program logic, and controls outputs to operate machinery with precision and reliability. Carbonatory key components. Every PLC system consists of 5 essential components. 1. CPU, Central Processing Unit, the brain that executes the control program and manages communication. 2. Input modules. These receive signals from field devices like sensors, switches, and transmitters. 3. Output modules. These send command signals to actuators like motors, valves, and indicator lights. 4. Power supply converts main AC power to DC voltage required by the processor and I/O modules. 5. Programming device, usually a computer running specialized software, where engineers create and edit control programs. Major brands. The PLC market is dominated by several major manufacturers, each with their own programming languages and features. Siemens' Simatic S7 series has become an industry standard across Europe. Allen Bradley's Control Logics and Compact Logics from Rockwell Automation dominate the North American market. Mitsubishi Electric's MELSEC series is widely used throughout Asia. Schneider Electric's Moticon PLCs, the original PLC inventor, and their newer M340 and M580 models. ABB's AC500 series offers scalable solutions from small to complex applications. Omron's CJ and CP series are known for reliability in diverse applications. How PLCs work. PLCs operate on a simple but powerful concept called the scan cycle, a continuous loop of 3 operations. Read. The PLC reads the status of all input devices connected to it. Execute. It processes this information according to the control program. Write. It updates all outputs based on the program results. This cycle typically completes in milliseconds, allowing PLCs to respond nearly instantaneously to changing conditions. Programming languages. PLCs speak multiple languages. 5 standardized programming methods defined by IEC 61131-3. Ladder logic. The most common method, resembling electrical relay diagrams engineers were already familiar with. Function block diagram, a graphical language that shows data and signal flow through blocks. Structured text, a high-level text language similar to Pascal or C. Instruction list, a low-level text language similar to assembly programming. Sequential function chart, perfect for sequential processes, breaking them into steps and transitions. Practical applications. PLCs are everywhere in modern manufacturing. They control assembly lines in automotive plants, manage conveyor systems in distribution centers, run batch processes in food and beverage production, coordinate robotic movements in packaging facilities, monitor safety systems in hazardous environments, working with PLCs. Now let's talk about how to actually work with these machines. Step 1. Hardware configuration. First, you'll need to set up the physical components, mounting the PLC, connecting power, wiring input and output devices, and establishing communication. Step 2. Programming. Using the manufacturer's software, like Siemens TIA Portal, Rockwell's Studio 5000, or Mitsubishi's GXWorks, you'll create the control program that defines how the PLC responds to different conditions. Step 3. Testing before going live. Simulate your program or test with actual hardware in a controlled environment. Step 4. Implementation. Deploy your program to the PLC and monitor performance during initial operation. Step 5. Documentation. Document everything. Future technicians will thank you. Engineering notes. If you're working with PLCs, keep these critical engineering notes in mind. Always include emergency stops in your design. Implement fail-safe conditions for power loss. Use latching circuits for critical memory retention. Isolate analog and digital signals to prevent interference. Design for noise immunity in industrial environments. Consider scan time limitations for high-speed applications. Implement proper grounding to prevent electrical issues. Use redundant systems for critical applications. Document your code with detailed comments. Information. Did you know? The first PLC was created in 1968 by Dick Morley for General Motors to replace complex relay systems that were becoming unmanageable. Today, one single modern PLC can replace thousands of mechanical relays and has transformed how we manufacture everything around you. Conclusion. PLCs have revolutionized manufacturing by replacing thousands of relays and hardwired control panels with flexible, programmable systems that can be updated with a few keystrokes. They're the quiet workhorses enabling the modern industrial world. Thanks for watching. If you enjoyed this video, please don't forget to like, comment, share, and subscribe to support the channel. Hit the bell icon so you never miss an update. Share this video with your friends. It really helps us grow. Keep me in your prayers. See you in the next one, coming soon.